You please hear me and see my screen. Okay, I see Ronfei already started the recording. Then we can start now. So at the beginning, please make sure that you have downloaded your input data file for today's exercise and prepared your computer with Abaqus. You can use Aalto Uni system, but if you use this one, sorry, I need to change my pointer. If you use this one, make sure that finally you do this send out instead of disconnection. So it will help to save this resources from this Aalto VDI system. And now we will start. So today we will talk about mainly the microscopic level because for the last 2 weeks, we mainly talk about everything about the microstructure. So from this week, we will go to a micromechanics part. First, I will give you a short introduction on micromechanics modeling and the definition of your task today. And then you will learn the FEM modeling with Abaqus. And at last, we will give a feedback on the assignment from last week. And you'll see this figure again. From exercise, we normally focus on the computational part. And today our focus is here. So we'll use the microscopic model to link your microstructural property, your mechanical properties like the flow curve to predict the component or structural level performance. And for example, if we focus a simple structure model like a structural geometry like this is called a central hole structure. It have a hole at the center of the whole bone sample. So the sample will be used for uniaxial tension like this. So we will tension along the rolling direction of this material. And normally we will focus on the critical deformation zone. So we will also define a so-called initial length, the L0 length, and we will focus on this area. So in experiment, we will get, after the tensile test, we will get the response force and displacement curve like this. And you will also get a deformed pattern or fracture pattern after the test finished. So at the same time, how we can also obtain these results from the simulation. Like this, first you need to generate your structural finite element modeling. And here, in your focused L0, in your focused L0 part, you can generate like this 1/8 of this 3D model. So you can only simulate 1/8 of it, then you can use the symmetry as your boundary condition. Then finally, you will also get the full model results. Or instead, if you want to certainly get the prediction of this, like it is not a final fracture along your symmetry plan, it has an angle with your horizontal symmetry plan. So you can generate your model with a full model in the critical deformation zone. And then you plus your structural model with your materials behavior model. So here we will have first a histoplastic model. It's like the Ms model here. Then after the prediction, we can get the response force and displacement curve with Ms model. And you see here with Ms model, there's no damage path. So you see the micro simulation result can give you a good prediction with your experimental result at the elastic and plastic part. But when your damage or after your damage happens, your model cannot capture the drop of the force. So furthermore, we will also have a kind of damage model. For example, what you learned from the literature, the EMW or JTA model. So with this damage model, you can see that it can predict this drop of the force caused by damage or final fracture with a quite good agreement with our experiment. And furthermore, after the deformation, you will see this deformed pattern. And this also have a higher agreement with your experiment. So this is normally what we do for micromechanics modeling. So first you need to build up a structure model, then you need to assign your materials behavior to your model, then you can see your predicted results. And today we will also do a similar task, but more simple. So because first you use a student version of Abaqus. So in the student version, there is a limitation of the maximum node you can use, that is only 1,000. And furthermore, because we have time limitation, so here we just give you a simple example to see how to generate a model with your Abaqus to do the FEM simulation. So we will use a quite a simple example to do it. For example, we focus on this whole central whole sample, but we will do it in 2D, and we will only focus on 1/4 symmetry part of it. So you will, based on this initial structure at the critical deformation zone, you will only model this part. It will showing like this as your FEM model. And we ask for a uniform or uniaxial tension along RD. This is your RD with a predefined global strain of 20%. Then with this condition, you need to know how to add your boundary condition to this model, and then how to add your materials behavior model to this FE structure model. Then you will get your final predicted result. We will have two kinds of materials behavior model. The first is Histoplastic Model. Here we will use the deformation criteria, and then it's a damage model, and here we will use the GTM part. And finally, you can see the prediction between with these two models. And you can see in the histoplastic part, there's no damage. And with the damage model, you can see final fracture pattern like this. And again, because of the time limitation of the exercise section, the second part will be given, I will give the slides to you, and it will be a self-learning part for you. So during the exercise, we will only learn, or I will like build you to know how to generate a model with the histoplastic simulation. And as I said, we will use the Abaqus 2020 student version. So now is about your software preparation. I guess you already finished this step. And then you can go to your computer and turn on your Abaqus software. I will also do the same for mine. So you see in the Aalto computer, you can directly click start. If you save it in your start menu, you can directly start the Abaqus AE. If it's not here, you can search for it, just type in Abaqus. And there will be a lot of Abaqus, Abaqus software in this package, Abaqus apps in the Abaqus package. And you only need to show that you can find the Abaqus CAE window. Then waiting for a while, we will check for the lessons. Here in your computer or in Aalto computer, the student version is already 2020. But I installed the Abaqus business version on my office computer, and the version is 2017. It doesn't matter, because for the simple test or simple example, there's no difference on the operations between different Abaqus versions. So you can just close this one, and then you will see a detailed of your normal layout of the Abaqus window. Go, sorry, no, this one. If you go back to this slides, so you start Abaqus, close and start session. And here is a general introduction of what you will see, the layout of the Abaqus. So you will have a lot of different bars here. There are many menu bars or some toolbox bars. You will also see your toolbox area in between. And the left part is a so-called model tree or result tree. So if you collect model, everything you can use here to generate your model. And if you collect results, then you can use everything here to see your results. And your model will show in this viewport. And the more important thing is that here in your message window, you will see your operation history. And if there are some warnings or errors, it will also show here. So please let me know that you have already turned on your Abaqus and see this general layout of it. Lucas, you are the first one. Wait for a while to see more students who join us. Available later when sorry, I can't get your question. What is available later? So just turn on your microphone and explain your question. Students is being.
So yeah, so my toolbars right now is like in the picture, but it doesn't have anything. So it will eat the toolbars will appear when we open the project or something.
You say you mean that you can't see these toolbars in your currently window?
Yes. My toolbars right now is empty.
Okay. There could be two possible reasons like this. You can change the layout here as you want. You can redefine everything or make it outside of the toolbar fixed area. It doesn't matter. And if you say, okay, I can see none of this, then you can click this view part and there is toolbars and click whatever you need.
Oh, I understand.
Yeah, okay. Only 4. I hope most of you can follow this section. It's not so complex, but you might face some small problems when you do it. So it is better if you can follow this session. I guess it's all these remnants, then I will just go on. So this is a general introduction of the workflow, how to set up a FE model in Abaqus. And I guess now at the beginning, you will have no idea about what I write words here or captions here. It doesn't matter. So after you follow this step by step, you will understand it better. And now I will just only give you a short introduction. First, that you need to build up the structure model. That is called part. Then you need to use assembly to link your materials property with that model, with your structure model. And you also need to use assembly to set your calculation step time or set your calculation step. You also need to assign your loading and boundary conditions to that model. That is mainly tell the structure model how you need to deform. And then you also need to match this area. That is the capital or the idea of finite element. And then you create a job or create an input file and submit this job. Then after simulation or after running, you will get the Odb files to see your results. And here, as I said, we will focus this whole central whole specimen, and this is the whole structure of it. But here we only need to focus on the critical deformation zone, and we will only generate a model of 1/4 of it with a 2D model, and we will set a symmetry line or symmetry plan along these two boundaries, so that finally your result is still responsible for the full model. And now we will start. The first step in Abaqus is normally set your work directory. So if you go down to your Abaqus software, you need to click first the file, and there is a set this one, set work directory, and click it. The default path is always in C driver, a so-called Abaqus tab or temp folder. If you know this path, you can find it. It's also fine. You can directly use this one. But if you say that it's not so good to save in C driver, then you can change it to whatever you like. So I will normally choose the driver and documentation. And then you need to, if you need to find a new folder for it, then you just create a new one. Create a new one and rename whichever you like. And here I already have it. So SEM E3. Then I select this folder, click OK. Then you see your new path is showing here. And then you click open OK to set this path. So after that, if you open this folder in your preset path, you will see everything will be stored here. But now I guess your folder is still empty. So you can download your E3 access flow coded here. We will use that part. We will use this file later. After you set all these work parts, then we can start the generation or set up of this 2D FE model. So you need to collect this part. So in this model tree, make sure that you are now in the model mode. In the model 1, double click these parts. And Abaqus will ask you which kind of part you want to generate. You can rename it or not, just use the default name, that's okay. Then here, as I said, we only need to use a 2D planar model. So click this one, and it will be a deformable model with a cell structure. And then you can also refine the dimension of your drawing paper later. So as you still remember, if you still remember the dimension, the longest dimension of the critical zone is only 10. So here we can define it like to 15, and then we can continue. After you click continue, you will see a drawing paper on your screen. So you need to join something or just join give a drawing of your geometry. So if you go back to the geometry part, this one. So as we explained, we will draw something like this with a 1/4 of it. It will be a cube with the length of 5 and width of 3. Then you need to also add a hole at this part. So this point will be your 0 point on the left bottom point. Therefore, if you go back to your Abaqus, you first click this rectangular, and your starting point will be this original point 0, 0, and click it. Then if you move your mouse, you will see a predefined rectangular will show it like this. Then you found this point, not this one, this one. So it should be with a width of 3 and length of 5. So you can see your position of your mouse will show on this left bottom or left top. Then you click this point, you will see a rectangular will become to yellow. Then you have already generated this part. And if you want to make sure the dimension or the size of your each lines, you just click this one, this add dimension icon, and choose your lines and move it. Then click it to fix it. So now it's already 3. It's already what we want. If it's not 3, you can change it here. And then you can use the middle part, this one, the middle bottom of your mouse. Just the middle click it, then it will be fixed in Abaqus. That means confirm in Abaqus. Then you can check another lines. Select it and click to confirm that the length is 5. And then still middle click this one to confirm. Like this.
I'm sorry. How did you make the red rectangle in the first place?
Sorry, I can't hear your question clearly.
How did you make the red rectangle in the first place? The red rectangle.
Red is just you click this rectangular.
Ah. Okay, okay.
Yeah. So I will show the slides to you again to see the operation. This one. So this is the first step to generate an outline of this designed geometry. And the next step is until we still need to generate a hole here. So for the central hole, we still collect this central point. We are use a cycle for this time and regenerate the cycle. And the next step is until after we define the cycle dimension, we need to delete all unnecessary outlines. So your final outline should be looks like that. Then let's go back to Abaqus to show you how to do it. You can use also your mid button of your mouse to zoom in or zoom out of your pattern. And here is a cycle. You click this one, create a cycle, and still choose this center point. And then you see you can define any cycle with any dimensions if you want. And now I select this one. It should be with a radius of 1. And again, you need to confirm it whether it's 1. So add a dimension, select this cycle line, you will see, okay, it writes down here, it is have 1, R1. Then confirm it. If it's not 1, just change it. And now you will see a overlapping outlines with these two shapes. Then we need to delete all these unnecessary lines. So there is an icon named by auto trim. Just click this one and move your mouse to your which dimension or which lines you want to delete. Select it, then it will disappear. Again, select this one and also this two small parts. So you will see the geometry like this. And you see your dimension is also being deleted with that one. If you want to see it again, you can add it again to this small part of the cycle. So this will be your final geometry drawing. After you have finished this one, you can directly save it, or you can directly again use your middle button of the mouse to confirm. So click this one, you see here. Abaqus will ask you whether it's finished or not, whether you have finished this section, then you can click down to finish it. So after I click down, you will see the 2D geometry or 2D part is already generated. And you can use your mouse, like use this one, is rotation view. You can rotate it and to see this view. You can see it is a 2D part with a dimension you define. Move it back to XY displacement review. So any more questions for the generation of the part? Or if you finish this step.
Yes. How do you generate this gray rectangle? I'm sorry.
It's first step, yes. So if you go back to the plotting of it, you mean this outline?
I mean, how do you generate? It's 3D.
Then 2D is not 3D. So in this drawing map, you need just click your mid button. So you need to click on the mouse. The Abaqus will ask you whether you need to confirm or not. So here you will see there is a done. If you add it or if you generate it, just click this down, that's fine. So everything should be already clear. And now I need to regenerate it. Then you will see this window.
Okay, I got it.
Yeah, great. So in all the operations in Abaqus, the middle click or that means done or confirm to next step. Then you will see your final part like this. And then we have finished the first step, generation a part. Then we need to assign first create our materials structure or materials behavior Then we need to assign this material behavior, that is mainly your materials model, to your part, to your structure model. So we need to go to this materials part. You can find this one in your model trees. So double click this materials. Abaqus will ask you the default name for it, and just use this one. And generally, you click this general. The first we need to give a density to this material. And this is steel. So we will use a mass density of steel. And in Abaqus, there is a deformed unit system like this. For length, it's millimeter, and Microscopic for stress, Newton, ton for mass, and this is second for type. So for steel, the standard density looks like that. And the unit is a gram per 3 cube of centimeter. Then we need to convert it to the Abaqus default unit system. So we will need to use this ton and millimeter. So you will finally get this value is 7.85 times 10 power of minus 9. And in Abaqus, you can directly use the 10 power of minus 9 to E minus 9. So you need to type in this part to your mass density part. Go back to Abaqus, it will be 7 point. So this should be dot, not comma, 85 E minus 9. So this is the definition of the predefined density of your mass. The first step, you need to define your mass. And then the next step is until we will tell the material how to deform. Here we will use the Histoplastic Model. So in the mechanical part, the first you need to choose the elasticity part and the elastic. And in the elastic part, there are 2 parameters you need to use. First is the Young's modulus. Again, the default Young's modulus unit is big Pascal, a big G-PAP. And here we need to use a MPa. So we need to convert this 20 ton, this is standard value for steel, to it should be 20 thousandths. And the Poisson ratio is 0.3. So here you collect this mechanical part, elasticity, always the first one, elastic. And Abaqus will ask you to save this, to input these 2 values. That will be 2, 1, 0, 0, 0, 0. So the unit will be MPa, and the Poisson ratio is 0.3. And that is for elastic part. Then we will also need to define our parameters for plastic part. So in the second one, you need to click this mechanical gun and choose the plasticity, a plastic part. And here you see the isotropic plasticity, that is Mrs. model. So you will need to input your yielding stress, and here you see this is a plastic strain to your window. Then you need to use the input date, what I given to you for the XS3. So please open the date file and copy the stress and strain date directly to this table. Show you how to do it. So again, mechanical, plasticity, plastic part. And you will see this MP now. Then you try to find where you saved that file. Open the data file. Say the first column is stress, and second project, actually this is plastic strain. Then you select all the dates with values, not. Please do not include in the first headlines. So the headers should be removed, then select all these dates. And Control-C for copy. And you select this window or this table, the first one, Control-V to paste it. So you will see all the values should be there. And then you can finally you define your density, you define the parameter for elastic part, you define your parameter for plastic part. And here you choose the hardening law with isotropic. That means for Mrs. model for histoplastic simulation. So that is already defined your material's behavior. Then you can click OK to finish this step.
Wait a moment.
Yes.
Oh, okay. Okay, no problem. I'm sorry.
Great. So any of you have questions on this part? If not, I will just go on. Any questions? I see someone just turn on the microphone. No? Okay, we will go on. So this part is only the to add or to define your material's behavior. So your next step should be you need to assign this material behavior or link this material behavior with your part, with your structure. Then how to do it? So if you go down to Abaqus, here you see your models are already turned this to property. If it's not here, just click this part and choose the second one, so property. And before you link it, you need to first generate a section for this model. So there is a second button named created section. Click this one and just use a default setting. So a default name of the section and it's a solid, then homogeneous solid. Then we just continue. And after you click continue, you will see there's only one material you just define. So just use this material 1. And you just can click OK. So this is the default setting for plane strain or plane stress condition. I'll show you a figure like this. So this is the generator section of it. And link this section with your materials. And your next step will be link the section with your final structure part. So after you create a section and link it with your materials 1, you will also see it in your module trace. So there will be section 1. And if you click this, you will see there's material 1. And then we need to use this one. It is assign section. That means you need to assign your section with your part. So click this third one, assign section. And Abaqus will ask you, you need to select a region to be assigned to a section. And also this region will need to be created to the set. So just we can directly use the default name for the set. And how you can select it is just move your mouse to your part. You see this part is being highlighted when you move your mouse here. Then left click it, left click it, or just click your mouse left button to select it. And then you can click this down or just use your middle button of your mouse to confirm. Then you will see this new window. It has been told you that you choose a region of set 1. It is showing in this color, and it will be assigned to your section 1. And this section 1 is what you just defined with this type, and it has a materials behavior or materials 1. Then you just click OK. You see, after you click OK, your part, it was in gray. And then after you assign your materials property or behavior to it, it will become green. For different displayers, the color will be slightly different. You will sometimes see something like blue or what, it doesn't matter. It's just not gray anymore. So that means you have successfully assigned your materials behavior or materials property to your part, to your structure model. So let's create a section, assign to materials 1, and then assign your section with your set. And then you need to assign finally your section and the materials behavior to your part, to your structure model. And that's the end of step 2. So make sure that you have already see this green model or this green color of your part. Make sure that you have successfully finished the assignment of your materials behavior to your model. Okay. So any questions for this part? If no, we can go on to step 3. So step 3 is a basic step for further operations to give your calculation step, or to define your boundary condition and so on. So that is generating instance in a assembly part. And this time we will go back to this model tree first. In my Abaqus, you will see there is assembly. This one, you can open it and create this instance. And you can do it either in the model tree, or you can also do it in here in modules. You just can choose this assembly. You say your model is disappeared because here you haven't generated any assembly or instance here. So you can double click this instance in this model tree to generate a new instance. And you will see your part shown here again. And here is only one part. We just use this one. Make sure that we need to use the independent bar. So afterwards, we will do the mesh on the instance instead of the mesh on the part. Then you can directly choose OK, click OK. So you can create it in instance and choose your part and choose the independent mesh type. Then click OK. Then is the generation of your instance. And after you do that, you will see a new materials coordinator of this instance. And here, when we generate this step, we do not do any movement or rotation of this part. So therefore, you will see this materials coordinator is consistent with your global materials global coordinator in Abaqus. So you didn't change anything, you just use a default setting. So after we create this assembly, we can define our step and mesh and so on. So this is a slide for this step. After you finish this step, we will go to step 4 and create a calculation step. So this step means calculation steps, and also define our boundary condition. And here you go back to your model tree. You will see your step. It's already there is a default step here. If you open it, it says the initial step. This is always a default initial step in Abaqus. And you go back to this step part, double click it. You will see a new step. So this will be your final step 1. It will insert it after the initial step. And here to save the calculation time. So normally you do a unit cell tension in Abaqus, you can use the statistic general to do your simulation or a calculation. But here to save the time, we will choose another one. So try to find this one, dynamic explicit. Okay, it can't be moved in this one. So you have to roll your mouse to find this one. Choose the dynamic explicit setting, and then choose continue. Here, the software will ask you which kind of time period you want to use. And here, the smaller, that means the faster calculation step. So we change this 1 second to 0.01 second. So try to define a small time period for your calculation to make it finish faster, and then click OK. So you will see after your default initial step, there will be a new step here. So it will look like that. To make sure that you choose a dynamic explicit step and change your time period to 0.01 second. And after you generate a analyze step, we can define a more related boundary condition or outputs for this step. The first is that for a dynamic explicit modeling, we need to add a amplitude to this step. So this is the definition to create it or add a amplitude. So you can find this amplitude here in your model tree in a quite lower part. Again, double click it, and you can directly use a default name and default type and continue. And here you need to give a table for it. You see we define a time from 0 to 0.01 per second. Then the table of time here is just 0 to 0.01. And we just use a linear amplitude of it. So just use from 0 to 1. And then after you define this amplitude table, just finish and click OK to save it. It will look like this. Any questions for this step? If no, I will just go on. So after you have generated step, you also need to define your output for this step. So which kind of value you want to obtain after your simulation. And here we need a stress, strain, force, and displacement. It's 4 variables. So first we need to find a stress and strain. If you go back to your Abaqus, there is called field output request. Then you can directly open it, and you'll see there is already for step 1. You need to double click this field output 1. And he will ask you, there is also quite a lot of default settings already saved here. We do not really need all these variables, so you can just click this small flag here, and then to remove all these variables. You see, I have canceled all the default values, and then I need to select what we really want. So you need to open the stress. You see there are different terms of stress. Of course, you can choose the third one. It means equivalent stress, but this one will only give you one value. So normally we will choose this one. So you will get a stress component and all the invariants that also it will save the missing stress in this part. And then if you go lower, you go to the strain part. And for the strain, of course, you can also use the same total strain component, or this one, the PE plastic strain component. And for strain here, we only focus on the missing strain. So you can use this PEQ. This is the equivalent plastic strain. That is directly your missing equivalent plastic strain. So click this one, you will see I have already choose stress and strain, that is PEQ. And then if you go lower, you will see the next one is displacement. If you open this one, just click the first U, that is what we made for a displacement part. And then will be the same for the force. The force is defined as the reaction force. So if you open this first term, there will be a first one, I. So you see this will be the 4 variables we want to have. You can directly choose it from here, or actually if you know the variable names in Abaqus, you can also use this add variables and type in these 4 terms. So it can be either here or here, it doesn't matter. And after you select all these 4 variables, so it's S, PEQ, U, and F. Here in between, there's commas to separate them. Then you can just click OK, finish the definition of your output or required output. Then you can see the slides here. So add this field output, you can double click either this F output or double click the step, that's the same. Then you will see it will, because there's only one step. So that's the same for whichever you want to initiate this process. Then select S, select PQ, next slide, select your displacement U, and select your force as a reaction force. And that will be all for a field output definition. And now we will define this boundary conditions, the BC as part. So if you go down to Abaqus, again in your model tree, in the lower part, there is a BCS. So that is for boundary conditions. Double click this one, and it will ask you which kind of boundary condition you will to have. So in this model, we want to do a uni-extension of it. And this model is also a symmetry model, as I explained, it's 1/4 symmetry. So you will need to add 3 boundary conditions in total in this part. The first 2 is a symmetry boundary condition. So along this line, or actually along this plane in 3D, you need to add a symmetry with respect to your X direction. So you can image that here is one part of it, then you should have another one in this part. So this will be your symmetry line. So the first boundary condition is add a X symmetry on this line. And similarly, you should also have a symmetry line along this part, the bottom outlines. So here is a symmetry with respect to Y direction. So it will be called Y symmetry. So you will need to select this one to add a second boundary condition with a Y symmetry. Then you will have this part of the model, then this part of your model. And the third one is finally how we can add the loading to this model. So the third boundary condition we need to add to the top of this model, it will be a tension. And here to simplify, to make this question simple, then we only need this displacement controlled boundary condition. So we will not add load, we will only add displacement to control the global strain what we want. So we will add a displacement deformation at the top line as a third boundary condition. So now we start with the first one. After you already double click this species, it will have a first default name of BC1, and it will be added to the step 1. And it is a mechanical part. The first, as I explained, we need to use a symmetry boundary condition to this line. So default the first one. Then you click continue. Then the model will ask you to select a region of the boundary condition. Then you need to carefully move your mouse to this outline. So do not choose all this one. No, this is wrong. Only make sure that this line is highlighted. Only this line, you need to add the boundary condition as highlight. After you see this one, you click it, and you need to rename it because the set one is already exists for the whole model. And this one is what we need to add a symmetry along X direction. So I directly renamed it to X symmetry. After you select it, you see only this line become red, and you create a set named X symmetry. You can click down. Then you will see a new small window. Abaqus will ask you to fill up the adding the boundary condition diagram. So you see here, this first boundary condition in step 1, your region is X symmetry. It is already highlighted in red in your model. And here you choose the first X symmetry. That is what will be added to this model, then or to this line. And then you click OK. After you click OK, you will see there are some small marks. This means the X symmetry part will be fixed to this line. So you need to only see the symbols for the asymmetry only on this line. So actually here. If you have already generated the asymmetry one, we will do a similar one for this bottom line. So it will be a symmetry line along y direction. So it will be named as a y symmetry, and it will be at the y symmetry boundary condition. So let's repeat this step for the second boundary condition. You double click again this B6. And you see the default name is already changed to boundary BC2. And it's still mechanical symmetry, then you can continue. And again, make sure that you only choose this line, not the whole model. So make sure that it's only highlight this line, choose it, and rename it to Y symmetry now. And after you select this region, it's highlighted in red, and it's created a set with Y symmetry, then you can click down. And for this boundary, second boundary condition, with step 1, the region is Y symmetry, and here you choose Y symmetry as your final boundary condition. And after you click OK, you will see a different symbols looks like this. So this orange one means which direction is your symmetry direction. So this is the first 2 boundary conditions. This to define this model will be a symmetry model. So you see with this one, you will generate a finally only 1/4 of a 2D model. And then we need to add a final boundary condition of it to control your loading. If you still remember, at the beginning, I asked for a global strain of 20%. Then how to add a global strain of 20%? In this whole model, the length of the whole model is 10 millimeter. So the global strain of 20%, that means you need to add a moment of 2 millimeter. And consider that this is only half part along your Y direction or along your length direction of this whole geometry. Then you only need to add a moment of 1 millimeter. Or in another word, if you consider only this half model, the length of it is only 5 millimeter. Then for consider a global strain of 20%. That means again, for this half model, you only need to add 1 millimeter as your moment. So we will go down to Abaqus, double click a boundary condition again. And for this time, we need to use the second one. So it's not a symmetry boundary condition anymore. It will be a displacement controlled boundary condition. So for BC3 mechanical, choose the second one, displacement, and then continue. Again, Abaqus will ask you which part you want to assign the boundary condition to. So here we need to select this top line. Make sure that you only select the top line instead of now like a whole model. So make sure only this line is highlighted. Click it and rename it to your set, like displacement or DST or load or whichever you want to use. But just remember the name of this one because you will use this set to extract your date later. So here I only use displacement, DISP. Then done. You see for this boundary condition 3, now this type is displacement or rotation boundary conditions. It will be assigned to the range, or you just define as displacement. The top line is highlight. And now we need to click which one we want to assign the deformation or assign the displacement. And you see here, this direction is Y direction. So Y direction is U2. You just click this U2, select it, and change it to what we want, so 1 millimeter. And for this calculation step, do not forget that it is an explicit, dynamic explicit step. So in Abaqus, you need to give a amplitude to this dynamic explicit step. Then you just collect what we have already predefined, the first amplitude. Click this one. So in this part, make sure that you choose the U2 with 1 millimeter and also select a corresponding amplitude. Then click OK. After that, you will see this upper arrows. It means that you have added this boundary condition. So this is the 3 steps to add a boundary condition of your model. And now you should see a figure like this to generate or assign all the boundary conditions. So any questions for this step? If no, I will directly go on. And now you will go to the final part for a idea of FE simulation, finite element. So how to really make a finite element in your model. So we will go to the so-called mesh part. In your model tree, in this model bus, you need to change your wheel to mesh. And you'll see your model, the boundary condition is disappeared, and your model is become to a pink one. Sorry. And first, you need to assign the type of mesh to which kind of mesh algorithm you want to use. So here it is this button, assign a mesh controls. Click this one, and here we just use the default setting. So use the free mesh, use the advanced defaulting, and you do not do anything here. Just click this assign mesh control, then click OK. That's fine. And afterwards, you need to give a roughly or predefined mesh size. So you need to go to the first one, a set part instance. So here we use a homogeneous mesh for the whole part. So we do not need to assign to every edge. So we only use the first one, set part instance. So we give a global mesh to it. And here, after I calculation, you know that there is a limitation of your nodes for a student version of Abaqus. Therefore, a roughly mesh will be given to 0.40. So then you can directly apply it. You see a small sys will appear on this edge or boundaries of your sample. Then you can just click OK. And this is not disappeared, it's just not shown now. So that means you have already defined the algorithm for your mesh type, then you have already defined your mesh size, then you can directly mesh it. So there is a second button called mesh part instance. So again, we will do a homogeneous mesh to the whole part. Click this one, and then just choose OK. Yes. You will see your mesh like this. So after you do the mesh, you can go to this information icon in your toolbar. You click this information. It will ask you which one you want to see. Select this mesh. And then it will ask you, okay, you want to see the whole sample? Yes, click done. And in this comments window, you will see Abaqus will tell you how many number of nodes and how many number of elements currently in your model. And you see this menu, this is what I tested for this geometry with this kind of mesh size. You can directly reach the maximum limitation of your node. So it's slightly lower than 1000. Then you can run this simulation in a Abaqus student version. So after we do the mesh, we already nearly go to the final step of your generation of your model. and then you can directly click a job and submit it. So you can close this information part, and then finally go to the analyze job part. Double click this job, just use the default one, job one, model one, then continue. As you not change the model name here, the default is model one, so it should be job one, model one, continue, and then OK. Then your job, you see in your command window, it says that job one has been created. And you can open this jobs and select this job one. Then you can right click it. There will be a date check. So this process will help you to check whether you made any mistake or errors during your generation of the FE model. So you can left click it, date check. It will say it will be submitted to a check. And you will see whether your input file is submitted to a check, to the analyze. It will running for a while, and later it will tell you whether your job is successfully running or no, sorry, successfully checking or not. So this is not a final job running system. It's just the first to check whether you make any mistake for your job. And if you see all this successfully, and also see a check complete, that means no error, no warning. So this job should be okay to run, or should be ready to run. If you see any warning message here, then you need to check what happens with it to modify your errors in this model tree again, then check it again. So any questions for this step? If you also say this successfully finished once, then you can left click it again. And now this time, we will choose submit instead of date check. So we can submit the job. And because you have already run a date check, so your input file is already there. So it will ask you whether you want to rewrite this output file, input file again. It doesn't matter whether you choose OK or not. So just rewrite it. Then you'll see job is submitted, and it will running for a while. So during this period, I just asking again whether there's any questions about the model generation. If sample for the student who has already successfully finished everything, just waiting for running, then you will have a 5 minutes break. We will come back at 11:24. So if you have any questions, you can directly also ask now. Or any step you cannot follow, I can change back to my slides if you want. Or if no questions, just a short break now. FEM simulation actually. So if you not follow it, you will see all the details here. And so afterwards, you can save your CAE model. So this model is called the CAE model with all the details options inside. Then you can directly save it, and next time you can open it if you want to modify the geometry or modify it slightly on your boundary condition and so on. You can do a modification inside and not instead of generating a new model. So to save it, you can just click the save button, and you see you should already in your work path as you predefined. If you are not there, you just click this small hammer. That means go to your work directory, and you can click it as now I'm already there. And then you can name your file with this for the CE model. And so it is for E3 central hole specimen. Then click OK. Then you will see your CE files within that part. So this is for save your CE. And the next step is that how you can see your output results from the simulation as it's already complete successfully. And then now you go to the result part, and you click open this button under this files, the second one. And you need to know that the output file in Abaqus is in the ODB type. So the first CAE, that is for your model database. And for then the second ODB, that is for your output database. Then you select this ODB, and we have renamed we not rename our job. So the default name for the job is job 1. So this job1.odb is your result file, result database. Then you select this job1 ODB, click OK. Now you see a new model or new result model shows in your viewpoint, and you will see it's already changed to this result part. And this is the initial state of this deformed model. Then you click this button, this 1, 2, 3, 4 button, that is a plot contour on the deformed shape. Then you will see, okay, now it's a deformed pattern. And this is the default deformed pattern displacement is only have a 1/4 of it. Then if you want to show the full model, you can go to this viewport. This one, view. And then you choose this second one. In the view menu, there is ODB display options. If you click this one, then choose the last tab, that is mirror. So that means you need to tell Abaqus for the output results, which one is your symmetry mirror, and it will show the whole model of it. And if you still remember here, this line is a mirror. So this line is on the YZ plane, and this line is also a mirror. So this line is on the XZ plane. So here you click XZ and then YZ, then click OK. You'll see your whole model like this. If you pay attention to the legend here, it's already as Mrs. So you can also see a small window here. Then it's primarily as Mrs. So that means this is already your Mrs. stress pattern. Then if you want to see your Mrs. strain pattern, you can choose this one. You see what we have defined as PQ. That is your Mrs. strain pattern. So you see this is a deformed pattern with Mrs. strain distribution. And you see because of the cross mesh we used here, because of the node limitation, it only shows that it's extremely elongated part or elements on the side. So you see, because this is a symmetric model, so anything I select in this 3 parts, they are actually not existed. So the only existed part is in what you generate this model in this right top one parts. So when I move my mouse to this element, actually it tells you that the element is here. And this is how to see the deformed pattern. Then you also need to know how to extract the force and dismember curves. Because of the time limitation, I cannot wait you to follow all the steps, but you will see that all the steps is saved in this slides. So if you can't follow it, you can do it detailedly, follow all the steps. And here I just show you how to do it now. And first, after you see this pattern, you also need to save this picture, not just use this screenshot for this one. This is not professional for your report. Then if you want to print or save this pattern, this figure, you just choose File, go to Print. Then a new window will save. And you choose this print to color with color print to a file. And you will do not need this all this background or something. Then you select a path. If you open this small folder icon here, it will select which path you want to save it. This is your default path for your work path. And this is PQ, that is Mrs. Student pattern. For this E3 axis. And you can directly click OK. And here you see a format. You do not use it. You do not need this PS format. You can just use the PNG one, and you do not reduce it to a standard colors. Then you can just click OK. And I will tell you that this sample, this picture has already printed to this path. Then in this folder, you will also see a picture of your Mrs. String pattern. And then will be the same for stress. If you change it back to S, you see there's a lot of output with different S components. You choose the first one, Mrs. S, and then you can save this figure again. You just rename it to stress E3 and click OK. Then it will save it again to your stress map like this. And if you see that one is not looks like look good, then you can also like move your button, move your sample close to your legend. You can also redefine the legend. Use like this one. You can choose your control options. You can redefine your limitation of your Mrs. String pattern control, like the auto maximum value, set it to like 1000, and you use the starting point of 0. Then you can apply it. Then you will see a different values will show here like that. And you can say I do not want to show all the details of this job here. Then you can also try to make this dispute. Use this one. There is a viewpoint option, and you see now everything has opened on this viewpoint section. You can just minimize or cancel this last series, then apply. It will be dispute. So it will only show this compress like this chart like the coordinator of your material, and also it will show a legend like this. So that's okay for all your 3 figures. Like you can zoom in or zoom out to make a proper size of it. Then you can print it again. If we see these 2 different, so there's a new one. Rename it as 1, and then OK. And if you compare these 2 figures, you will see this one will be a more professional one to show in your papers or in your report. So that's a slightly changed on the layout of the how to save this figure or how to make your figure more properly. Then we will know how to extract the force and displacement date. So now you need to go to this create XY date. You select this one. The second one, field output. If you still remember, we defined the field output with stress and strain and force and displacement in the model tree. So now we also choose the second one, field output, then continue. And here for positions, we need to extract all the data from the unique node position. And then we need to have a force and displacement. They are all along Y direction. So then will be a RF2 and U2. And then we go to a second tab, that's the element tab. There is node set. So we need to extract all the dates for the top bottom of it. Then we just select this, what you have renamed that set when you define this third boundary condition. And highlighted, you will see, okay, this bottom, because this is a symmetry viewport, so you will see it in these two outlines. So actually, in the model, it is only in this half part of it. Then you save it. Abaqus will ask you again whether you confirm this kind of restriction, and click OK. And then if you click this button, there's manage your XYZ date, you will see, oh, every date from the RF and U2 date from all this calculation integration point has been extracted, but they are date at each point. Globally, we need to obtain the homogeneous or global force and displacement of the whole model. Then we need to do a external or additional calculation on it. Then will be, you go back to your create XY date again. There is an operation or operator on XY date. Then you can continue. Here there are different mathematical functions you can use here. You can image for this whole model. I can first make it displacement without this measure to make it easier to understand. So this is what you really have on your model and what you really have for this data set. Then you can think about how you can do the homogenization to obtain your global force and displacement. Actually, it's quite easy. For force, you can image if you have a force on each point, then your global force should be a summary of all these points. But for displacement, if you have a displacement value on each point, then you need to do an average of all these points or all these values to get the global displacement. So we'll do it for force again. First, you click sum. You see an equation is being here, and you see your mouse is at the position enter this brackets. So you select all this force state, try to select, make sure that you select all force state. You shift on your keyboards. At the same time, use your left click mouse. You have select all this RF date, then add it to its expression. And you see this is already a function of with all the summary of all nodes of the force F2. And in addition, if you remember, this is 1/4 of your model. So this is only half part of your force along your y direction. You still have additional half part here. So that means for a global response of force and displacement, you need to type with 2. Then will be your final force for the whole model. Then you save it to force. Click OK. Then your force state has already generated. Then you clean this expression. Then we need to do it again for displacement. As I mentioned, for displacement, it will be average. So try to find this average function, click it, and then try to select all this displacement date, add it. And again, the same for displacement. You will see this is only the displacement for this half along the y direction. Actually, there still have additional half of it. So the global displacement is also need to be typed by 2. Then you save this one as your displacement date. Then you click OK. Then you will have a data set of force and additional data set of displacement. Then you need to plot this one. In Abaqus, if you only have this force and this force and displacement curve, if you plot it, there's only a single variable. Then if you want to plot them together, like plot your force as y-axis, plot the displacement as x-axis, you need to combine them first. So there is a function called combine. Then you define your first axis is displacement. Add. And then the second variable, the y-axis is force, then add. So you combine the experiment and force state. Then you can save it to plot. So this is only for plotting. Then you can click OK. Then you can close these two windows. You see in your XY date manager, you will see this plot again. Then you choose this plot and click this then plot. Now you will see, we can close all these windows. You will see the plotting of your force and displacement curve like this. And you will see your final displacement is finished until or roughly until 2 millimeters. So that is global strain of 20% based on your initial length, LDL. And if you do not want to show this figure only in Abaqus because it is really not a cubed plotting, it's just to give you a first image how it looks like, then you can output or export your XY date to save it. So there is a report XY. Then you select your displacement and select force. Then you go to setup. It will the default save a part of the name and the type is Abaqus RPT. Just cancel this one in order to make sure that it is overwrite every time. Then you just click OK. It should be already be saved. Then you go back to your work folder again. You found that name under it is Abaqus RPT. You need to open it in Notepad. You will see here your X is your time, step time, and then you will obtain the displacement and force state. Then you can replot it with Excel or MATLAB or whichever software you want. Then finally, you will see, sorry, I go back to my slides. And finally, you will see a curve like this. You can replot your force and displacement part. And this one, as I have already explained, we have until now we have finished all the analysis of the histoplastic model. If you are interested in the JTN model, you can follow all the detailed steps here. Generally, they are the same. You only need to modify a little on this several in this sub steps. And after that, you will again see your deformed pattern. There are difference between them. If you only have a histoplastic deformation, there's no damage. If you have a JTN damage model, you will see a new pattern like this. This is for your stress, and this is for your strain. And then later, you will have a comparison between your force and displacement curve. And in your exercise, you only need to do the histoplastic, that is Ms simulation. You do not really need to do the JTN model simulation. Here it's just if you are interested in this part, you can learn how to do it in Abaqus. So that will be all for today's simulation part. And additionally, in case someone forgot how to set your work directory or how to find your files, so this is a short introduction on how to find your work parts and how to find your files. If you forgot it, you can also check these slides.